Bismillah ar-Rahman ar-Rahim, and welcome to lecture number 24 for basic engineering mechanics. In this lecture we would continue our discussion of structural analysis, and we will discuss something which is called zero force members, and then we would see another method for analyzing the stresses and tensions inside of a truss using the method of sections, and then we'll look at some examples related to these two topics. Okay, so let's start with the first topic, which is called a zero force member. So basically there are times when we have a planar truss, and some of those planar truss members are basically zero force members, which means that there is no force acting. They're not providing any pulling force, and they're not providing any pushing force. And if we were to analyze, if we are able to identify these zero force members, our calculation and our analysis would be much easier. So let's see how we can identify a zero force member in our truss. So the general rule is that if we have three members at a truss joint, so any point of our truss where we have three members, and if two of them are collinear, that means that two of them they are along a straight line and there is no external force at that joint, then the third member would be a zero force member. Okay, so what does that mean for our case? That in this diagram we look at this joint at D, and at this joint we basically have three trusses. We have three truss members. We have ED, truss member ED, and truss member DA, and the truss member DC. But two of these members, ED and DC, these two members are collinear, they are along a straight line, and this third member is not in that straight line. Then this third member would actually be a zero force member, and it's not very hard to see why that should be the case. If we were to analyze this part of the this joint D, and as we already know that we can choose our x-axis and y-axis whatever way we like. So if we were to say that this is our y-axis and this is our x-axis, so we say that at this joint we would choose this to be our x-axis and this to be y-axis, and at this joint we would have three forces. Let me just change color and draw the three forces. We would have the force DE, we would have the first force, we would have a force along DC, and then we would have a third force along DA. Okay, and now that we have drawn all the three forces, we can, let me just also name them. So this is force DE, this force is DC, and this last one is actually DA. Now I can use the two equations of equilibrium. So the first one would give us sum of all the forces in X equals to 0, which basically implies that FDE minus FDC has to be equal to 0, which basically means that FDE is equal to FDC. And if we were to apply the second equation, sum of all the forces in Y equals to 0, and then the only term here would be FDA is equal to 0. That means this member would be a zero force member. We can do the same analysis at this point at joint C also, and in this case our equation would simply become sum of all the forces in Y would simply mean that FCA times sine of theta is equal to 0, which again would imply that FCA should be equal to 0. Okay, so it's not very difficult to see if the above conditions are true, then the third force member would actually be a zero force member. Okay, so this in this case, this joint, as we saw in the previous slide, this at this point D we have a zero force member. FDA is actually equal to 0, and in the other joint we have FCA is actually equal to 0. So another important point to make here is that zero force members, by the looks of it, it seems like in any truss, zero force members would seem to be pretty useless. But we have to understand that whenever we are building a truss, we have to consider that there might be any loading on any of the joints at any point later. And whenever there is any loading at any joint, these zero force members would be able to support those loadings. Okay, so just because they are zero force members in any particular case does not necessarily mean that they are useless. Okay, and we should not remove them from our system. Okay, and so another example for a zero force member is this example here. Using the method of joints, determine all the zero force members of the Fink roof truss shown in figure 6-13a, and we have to assume that all the joints are pin connected. So in this drawing we have two active forces, one 2 kilonewton force and a 5 kilonewton force, and then we have a pin support at one side and a rocker support on another side, and we have to determine any possible zero force members. And so first of all, let me start by looking at this joint at G, and what is obvious here is that there are only 3 members at this joint. So the first condition is true, and 2 of these members are collinear. So the member GH and the member GF are collinear, which means that the member GC, I can say that FGC is actually going to be equal to 0, or we can say that the GC member is a zero force member. Okay, and so one of the zero force members is this member here. This is a zero force member. And secondly, we can look at this member, this joint at D. Again, here we have 3 members, and 2 of the members are collinear. There is no external force. Then this third member should be actually a zero force member. This means that DF is a zero force member. Okay, so now that we already know that this one is a zero force member, and if we now look at this CF at joint at F, then it seems to have 4 joints, but one of them is already a zero force member and 2 of them are collinear, which means that the fourth one also should be actually a zero force member. So this is also a zero force member. So we can say that FC is also a zero force member. Notice that now that we know that these 3 members are zero force member, the rest of the structure is much more simplified, and it is much easier to find the unknown forces and stresses and strains in all of these other members. Okay, so zero force identifying, just to reiterate, if we are able to identify any zero force members in our truss early on, that would greatly simplify our calculation for the rest of the remaining truss. Okay, so now that we know about zero force members, now we look at another method. So as we saw in the previous example, these are the zero force members. These three members are actually zero force members. Okay, so previously in the last lecture we discussed the method of joints to solve for equilibrium of any truss, but now we want to find there is another method to find the internal forces, which is called the method of sections. So basically it involves breaking down our truss into smaller sections, and in a way that the internal forces then become the external forces and we can analyze them. So basically what we want is that if we have any member which is under tension, and so that tension would be equally divided throughout the member. If I were to break this member into two, if I were to cut this member from the center, this member there would be a tension on both ends which would be equal and opposite. Okay, and similarly if we have a member which has a compressive force acting on it, then if we were to break that member, that compressive force, if we were to cut that member, that compressive force would be acting on both sides. Okay, so in this way, even though this is an internal force, if we were to cut our member, this now simply becomes an external force, and they have to be equal and opposite just by Newton's law. If they are not equal and opposite, we will not have equilibrium. Okay, so how do we use, what is the method of sections then? Anytime we have a bigger section, first of all we would treat this as a rigid body, and we would find all the unknown forces using our all the methods that we studied in chapter number 5, where we were to find all the support reactions at D and all the support reactions at E in this case. Once we know all the external forces and we now want to know the internal forces, what we can do is we can cut our truss from any section. So we can say that we are going to cut our truss from this point A. So we want to cut through here, and now we basically make this into two different trusses, one on this side and the other one on this side. And we know that all of these members that I am cutting, there would be a force along that member in the direction of the member. So once I cut it, there would be a force FBC acting along the BC member, and an opposite force would be in the other direction on the other member also, the other truss also. Similarly, there would be a force FGC and there would be a force FGF. Okay, now this I can analyze. I can apply the equations of motion on this part separately, and I can apply the equations of motion on this part separately. And as this part has to be in equilibrium also, and this one has to be in equilibrium also, now these three forces become external forces, and I can simply use the three equations of motion: sum of all forces in X, sum of all the forces in Y, and sum of all the moments at any point, maybe C, is actually equal to 0. So now these the actual internal forces, by dividing our truss into different sections, we are exposing the internal forces and making them as external forces, and we are just solving for them using all the techniques that we studied in chapter number 5. Okay, so let's see an example. So again, what is the procedure of analysis if we were to do the method of sections? First of all, we decide the section of the truss, and then we determine, first of all, we determine all the external reactions using all the techniques we studied in chapter number 5, and then we divide the truss into different sections, and we draw the free body diagrams of each of the section, and then use the forces, use the equations of equilibrium to find the unknown forces in the members. Okay, so and then we write the equations of equilibrium, and we use those equations to find all the unknown forces. Okay, so now we look at one example. We want to determine the force in the members GE, GC and BC of this truss and indicate whether the members are in tension or in compression. Okay, so now we have this rigid body, which is the truss, and we have a pin support at A and a roller support at B. The first step again is to solve for the unknown forces. We would have a force along AX and AY, and then we would have a force along which is perpendicular to this roller. So the unknown forces would be AX, AY and FD. FAX, FAY and FD. Okay, and now we can solve, we can use the three equations of, because this is the coplanar system, we can use the three equations of equilibrium to solve for FAY, FAX and FD. I'm not going to do that calculation again here, because I'm sure all of you are pretty comfortable with that by now. And so using these three equations of equilibrium, we find all the unknowns. We know that AY is actually equal to 300 Newton, DY is 900 Newton and AX is 400 Newton. So now we know all the support reactions acting on our rigid body, and the next step again now is to divide our system into two sections. And as it is obvious that it's best to divide our truss into two sections from somewhere here. In this case we would get three unknowns, and as we already know that using a coplanar system of equations we can solve for three unknowns. So we divide our, so this is the first part of the truss, and then we apply the equations of equilibrium, and the equations of equilibrium we try to use here is the force in along the y is equal to 0, and the moments at two different points is actually equal to 0, and then we use these equations to find the unknown forces, which is FGC is equal to 500 Newton, FGE is 800 Newton and FPC is 800 Newton. Okay, and so this is how we find all the unknown forces in all of these members. There is a point to be made here. Let's just recap. And we have some a zero force member here also, because of, if we were to look at this joint B, we can see that there are only three members at this joint B. There is no external force and two of these members are collinear, which means that this member GC is a zero force member. Okay, so this is how we use the method of sections to find the forces and tensions and compressions inside of our members in our trusses. Okay, so that is it for today. I will see you in lecture number 25 inshallah. Assalamu alaikum wa rahmatullahi wa barakatuh.